Okay, so this is the population ecology video number 2. We're just going to finish up a couple of slides here. So we're going to look at factors that limit population growth. You are going to have two types, density dependent and density independent. Now density dependent factors, obviously the population is going to matter. For example, we have predation, population matters for disease, competition, physiological factors, things of that sort. Density-independent factors are factors where the population isn't a factor. It doesn't matter. Things like natural disasters, fires, floods, blizzards, hurricanes, tornadoes. Doesn't really matter what the population is if those density-independent factors occur. So we have two types of species. We have K species and R species, or K selection and R selection. And K selection is when the population is close to carrying capacity, and R selection species are species that maximize reproductive success. So what I'm going to have here is a chart, and you're going to want to pause the video and possibly write this down in your notes so that you have it. Again, you have K selection species and R selection species, and you can see the differences between the two. So for the R species, they love to grow as quickly as they can, hence that exponential growth. They don't really give a lot of care to their offspring. They have a lot of offspring at once, and obviously with a lot of offspring at once, the death rate is a lot higher for infant mortality. And then K species have a slower growth rate. They tend to give a lot of parental care. They invest a lot of energy and time into their offspring, and there's a gradual increase in the population. The example I have for the K selection species would be humans, and for the R selection species would be those pesky cockroaches. So populations fluctuate due to biotic and abiotic factors. Here we're going to review this particular graph. Remember, this could show up on your test, not this specific graph, but being able to read figures and etc. from your book. Here we have the fluctuations between moose and wolf populations from 1955 to what looks to be 2008. And down here at the bottom where your screen is cut off, it says 1995, harsh winter weather, deep snow. So in the case of moose, predation is an additional factor that regulates the population. Wolves rely on moose for most of their food. Because the lake they lived near has not frozen over in recent years, both populations have been isolated from both immigration and emigration. Even still, the moose have experienced two major increases and collapses during the last 50 years. The first collapse coincided with a larger wolf population, lowering the moose population. You probably guessed what happened. Here's our blue is our wolves and red's our moose. Lots of wolves here, not so much on the moose front over here. And then when we follow the moose, here's our second peak. The second one around 1995, so here's the second problem area where they decreased, was due to harsh winter weather, which made it harder for the moose to find food, and they honestly just died off. So this is just an example of looking at a graph and being able to decipher what is there. Is it necessary? Do you need to know about the harsh winter in 1995? No. But you need to be able to realize when you look at this, oh look, this is a dip in the moose population. Oh look, there's a lot of wolves there. Money has it that the wolves ate the moose. And then over here you just kind of obviously want to look at how, weather maybe played a role because there's not that much of a difference between the two populations. So for this slide, you're going to look and see and write down what you see. Write down some guesses as to why population rose or declined. You're going to pause the video and write down your thoughts in your notebook. So here we have the classic boom-bust cycle we see in a particular predator-prey interaction. The lynx are predators that specialize in preying on snowshoe hares. You're probably looking at the graph and wondering, why do the hares' populations rise and fall in approximately 10-year cycles? There's basically three hypotheses that have been proposed. One, cycles may be caused by food shortage during winters. These hares eat twigs and small shrubs. Two, cycles may be due to predator-prey interactions. There are other predators other than the lynx who eat hares, and maybe they overexploit their prey. And number 3, population size may vary with sunspot activity, which undergoes cyclic changes. Long story short, when sunspot activity is low, there is less atmospheric ozone produced, so more UV radiation hits the Earth's surface. Therefore, plants produce more UV-blocking chemicals and fewer chemicals that destroy plants, which could increase the quality of hare food. So here we have human population growth. So there's 2 configurations for stable human population with a 0 population growth. Obviously we have a high birth rate, high death rate. Then we have a low birth rate, low death rate. And then demographic transition occurs when population goes from A to B. Age structure is a relative number of individuals of age in the population. Typically, age structure diagrams look like the pyramids you see in front of you. So we're going to look specifically at the U.S. right here. The age structure for the U.S., seen in the middle, is relatively even until the older post-reproductive ages, except for that bulge in the middle. There it is. Which is from the baby boom that lasts for about 2 decades post-World War II. During those years, the nation's overall birth rate still exceeds the death rate because some boomers and most of the boomers' offspring are still of reproductive age. The population of the U.S. is projected to grow slowly through 2050 as a result of immigration. It's interesting, you can look here at Afghanistan, who has rapid growth, but most people are dying in around 80. And over here in Italy, there's really no growth at all. So global carrying capacity. The UN predicts that 7.8 to 10.8 billion people by the year 2050. In 2012, there was 7 billion people. The estimated carrying capacity is around 10 to 15 billion. The ecological footprint. This is the total land plus water area needed for all resources a person consumes in a population. Essentially, we've been told that 1.7 hectares, or little h, little a, per person is sustainable. To give you an idea of the size of a hectare, think of a traditional oval 400-meter track. Visualize the inside of that track with the grass. That is about 1.12 hectares. So they're saying that a little bit more than that is sustainable. In the U.S., there's about 10 hectares per person. Is that over the carrying capacity? Are there limitations? Consequences? Solutions? So here's a map of an ecological footprint of countries in the world. And as you can see, we have America, or North America, I guess would be better to say, in purple, bulging compared to Africa, which is shriveled up. And remember that the ecological footprint is the total land and water area needed for all the resources a person consumes in a population. So this just kind of gives you a bit of a perspective in North America compared to, say, South Africa. So that's it for our PowerPoints. Hopefully you wrote down questions, and you can feel free to email me or bring them to class and we can discuss them then.